The seventh lecture on Lagrangian mechanics. Today we shall extend the Lagrangian mechanics for non-holonomic system. To be specific, we consider those non-holonomic systems for which the equation of constraint can be put in the form of Pfaffian or differential form, but not of integral form, but which cannot be integrated out. As for example, the equation of constraint, equation of constants may be put in the form like this. With I is equal to 1, 2 up to k, the number of constants. K is the number of constants. So this is a and m is equal to 1 when the number of degrees of freedom of the system. So this is a constant. It is called non-holonomic constant. It is in the differential form, but it is not integrable. Not integrable. Let us cite few examples. Consider a constant of the form x dx plus y dy plus z dz minus c square t dt is equal to 0. This is a equation in this form, and if we integrate it, we get x square plus y square plus z square is equal to c square t square. It can be integrated, so it is not a non-holonomic constant, it is a holonomic one. So this is not a holonomic constant. We do not consider such types of constant. Let us consider another example. This is x square plus y square dx plus y dy is equal to 0. This cannot be integrated out unless we know the dependence of y on x or x on y. So this is an example of non-holonomic constraint. Non-holonomic constraint. Let us cite few examples from mechanics. Say we have a hoop or a cylinder or a sphere rolling down an inclined plane. So this is as the radius is r. If we call this angle is d phi and the perimeter is dx, if we call it dx and if we radius be r, then dx is equal to r d phi. So it is a constant, this is the equation of constant, but we cannot integrate it to get relation between x, r and phi unless we know the exact dependence, temporal dependence of theta and x on time. So this is an example of non-holonomic constant. We consider under this heading we consider such constants only. So with this introduction to non-holonomic non-holonomic constant, which can be expressed in the differential form but not integrable, we consider only those type of holonomic system, non-holonomic system. So the equation that we are going to discuss is which can be differential form, differential but not integrable form. constant size. For virtual displacement, we have the virtual displacement takes place at a particular instant of time, so dt is equal to 0, and we dq now is denoted by delta qm. That is to distinguish between the actual displacement and real displacement and virtual displacement. D are replaced by delta. The virtual displacement are displacements which are in accordance with the forces of constant imposed on the system but takes place at a particular instant of time. So for virtual displacement, the equation of constant becomes summation over AIM delta qm sum over I is equal to 1 to n is equal to 0. There are m is equal to 1 to n, and there are k such equations if there are k constants. As for Lagrange's method of undetermined multiplier, we multiply e by lambda I, sum over I is equal to 1 to k, and integrate it between over dt between limits t1 to t2, and it will have a fixed value. The fixed value is 0. This is the fixed value. So the Hamilton's principle, coming to the Hamilton's principle, this is J, the action integral of L dt from t1 to t2 is to be extremized, that is to say delta has to be 0. Basically this is delta r, lambda delta r. So this equation leads to Euler-Lagrange equation of the form summation integration over d from t1 to t2 summation over n from 1 to n del L del qm minus ddt of del L del qm dot, this is dot delta qm is equal to 0, and if we add this to this, we get integration. So integration from t1 to t2 summation over n is equal to 1 to n. Then we have qm dot plus summation over I lambda I AIM delta qm is equal to 0. I is equal to 1 to k. This is the integration over the equation of constants, and this is the integration summation over the equation of constants, and this is the summation over degrees of freedom. As per the basic theorem of variational calculus, these delta qm's are independent of each other, all this, so that this quantity must be 0. And so we have ddt of del L del qm dot minus del L del qm is equal to summation over I lambda I AIM. This is the equation, and there are in such equation because m ranges per dual. So there are in such equation. So this is the Lagrange's equation for nth degree of freedom as applicable to a non-holonomic system for which the equation of constraint can be put in the differential form, and for the system to be non-holonomic it must be the differential equation. The differential equation representing the constant cannot be integrated out. So this this is the equation we were looking after. If we compare this equation with the Lagrange's equation having non-conservative force, or in terms of force, then we know that it is the Qm, the generalized force corresponding to mth degree of freedom, where Qm is that part of the force, generalized force, which is not included in the Lagrangian. So if we have the force acting on the system which is partially conservative and partially non-conservative, then the conservative part is represented by the potential, and it is included in L via TL is equal to T minus B, and the non-conservative part of the force leads to the generalized force. We call that Qm is equal to summation over J Fj, force on the jth particle, del I del Qm. This is the force, and this is the generalized force. This is J, this is also J, and sum is over J. So this is the generalized force corresponding to the part of the force which is not included in the Lagrangian. So we may treat it as the force of constraint. So force of constraint is this much. So force of constraint for mth degree of freedom is Qm is equal to summation over I is equal to 1 to k lambda I AIM, where AIM are the coefficient of dQm in the equation of constant. So the equation becomes like this. So the Euler-Lagrange equation for a non-holonomic system can be written as ddt of del L del Qm dot minus del L del Qm is equal to summation over I lambda I AIM, which is identified as the force of constraints. Force of constraints. So let us apply this theory to few simple problems. Firstly, we consider the simple harmonic, simple pendulum. Earlier, we have considered a simple pendulum to be one for which the length of the rope or length of the string is fixed. Here, we treat the simple pendulum. We revisit the system in another way using this method. is the pendulum of length L, and this is the arc length, this is the angle theta. If we consider the particle of mass is over here, when the mass is over here and its coordinate is r theta, so the kinetic energy, if we write it Lagrangian is half m r dot square plus r square theta dot square. This is the kinetic energy part. If we consider potential energy to be 0 over here, then the potential energy is minus mg r cos theta. So minus plus makes mg r cos theta. This is the Lagrangian. So, and the equation of constant is the equation of constant is r is equal to L, or we write it as dr is equal to 0, so that we get ar is equal to 1 and a theta is 0, because there is no theta bar, d theta bar in the equation of constant. Now we come to the calculation of del L del R. Del L del R as per this equation is mr theta dot square from this part, and from this part is mg cos theta, and del L del theta dot is equal to mr dot. So the equation ddt of del L del R dot minus del L del R is equal to lambda AR. This gives you ddt of mr dot, this is for this part, minus mr theta dot square minus mg cos theta is equal to, since AR is 1, it is lambda only. Now we put the equation of constant that R is equal to constant and is equal to L, so we get this gives us R dot is equal to 0, R double dot is equal to 0. So this part is 0 because of the equation of constant, and if we put area R is equal to L, this equation becomes ml theta dot square plus mg cos theta is equal to minus lambda. This is one equation, equation AC. And now come to the second equation. Del L del theta is equal to, the L is this, so this is minus mgr sin theta, and del L del theta dot is equal to mr square theta dot. Now the equation of motion is ddt of del L del theta dot minus del L del theta is equal to lambda a theta. Since a theta is 0, we get from this equation ddt of del L del theta dot is equal to mr square theta dot minus this, there is a minus and this minus makes it plus This is mgr sine theta. So sorry, the sine is plus and sine theta is equal to 0. As r is equal to constant and has the value L, this equation we get m L square theta naught plus m g L sine theta is equal to 0, as r is equal to L is equal to constant. So that we get theta double dot plus g by L sine theta is equal to 0. This is not a simple harmonic oscillation. If we approximate sine theta by theta, then it would be a harmonic oscillator. Otherwise, it is an anharmonic oscillator because sine theta has term theta, theta cube, etc. If we could solve this equation for theta, hence we get the value of theta dot. When we put the value of theta and theta dot over here, we get the force of constraint. So the force of constraint can be obtained from this method. As the second example of non-holonomic system, we consider a cylinder rolling down an inclined plane, rolling down without slipping down an inclined plane. The situation is that this is if we consider this is the cylinder of radius, say small r. In that case, as the cylinder rolls down, the sectional view is this. This is the cylinder of radius r, and this angle, if this angle be d phi, then the arc length is dx. Then dx is equal to r d phi. So this is the equation of constant, and we write dx minus r d phi is equal to 0, so that or we can write it other way around, r d phi minus dx is equal to 0, where a phi is equal to r and ax is equal to minus 1. This is the equation of constant. So the equation of constant is r d phi minus dx is equal to 0, which gives a phi is equal to r and ax is equal to minus 1. Now we have to construct the Lagrangian. For the construction of Lagrangian, we call BAB, the length AB is L, and the length AP is X, so that BP, the length BP is L minus X. The cylinder is assumed to start rolling from A, which was at rest over A, and starts rolling down. So the kinetic energy will have two parts. One, the kinetic energy T is the kinetic energy of translational motion. This is mx dot square plus the kinetic energy of rotational motion I phi dot square. Now I is, we can rewrite it as half mx dot square plus half m k square phi dot square, where k is the radius of gyration. There are three types of simple geometry may be there. This may be a solid sphere. Solid sphere of radius r, in which case k is equal to 5r square by 2. Let me check. Sorry, this is for a solid sphere, this is 2r square by 5. For a solid cylinder, which we are considering in this case, it is r square by 2. R square by 2, and for a hoop or ring, it is simply r square. So three different geometries may be there, and correspondingly k will have different values. And the potential energy, if we consider this is the zero level of potential, then potential energy is mgh, where h can be written as sine of alpha is h by the, so h is equal to L minus x sine alpha. So with this we write Lagrangian. To save space I am omitting this part, and for cylinder we write, for cylinder k square is equal to r square by 2, simply for cylinder. Now the Lagrangian is t minus b, so this is half mx dot square plus half m k square phi dot square minus mg L minus x sine of alpha. So the first let us calculate del L del x. Del L del x, there is no contribution. Here is a contribution, this is minus minus plus sign. So this is mg sine alpha. And del L del x dot. Del L del L next dot is mx dot. So the equation is ddt or del L del x dot minus del L del x is equal to ax lambda, since there is only one constant. So for this it is mx double dot, and this is minus mg sine alpha, and ax is minus 1, so this is minus lambda. This is equation A, first equation. And del L del phi, del L del phi is 0, and del L del phi dot is equal to mk square mk square pi dot. So that the equation is ddt of del L del phi dot minus del L del phi is equal to lambda a phi, where a phi is r. So if we put this, we get ddt of mk square phi dot is equal to r lambda, or the equation of motion, this equation of motion is mk square phi double dot is equal to r by lambda. Now this equation is the equation for B. This is the equation for B. If we write this equation for the cylinder, this is r square by 2, or so this is m half m r square phi double dot is equal to r by lambda, so that we get or r phi double dot is equal to 2 lambda by m. This equation is only for cylinder. Now the equation of constraint is this. We can write the equation of constraint can be written as r phi double dot is equal to x double dot. The equation, we can get the value of x double dot from equation A, and we get the equation of phi double, the expression for phi double dot from C, and we can put here to get an expression for lambda. So which enables us to find out the value of lambda. On simplification, lambda becomes for cylinder half mx double dot is equal to 1 by 3 mg sine alpha. So this is the first class on Lagrangian mechanics on non-holonomic system. In the next class we shall cite few more examples for non-holonomic system.